Welcome students. In today's class, I am going to discuss Hughes algorithm for multiprocessor scheduling. So, as you recall in the previous class, I have discussed that in general my sequence graph is a graph where the nodes have a different delay and the type of the operations also delay is different, right. But if you take some restrictions or some assumptions on this particular input graph, that if this node type is same, that all operations of same type or it can be executed using a multiprocessor. So, this is my assumption 1. Second is that this delay of the operation is all 1, that means I have a unit delay. And the third assumption that I have taken, that the sequence graph is actually tree. The big difference from the tree and graph is that graph can have from any node to sink node there may be many paths, but in a tree from any node to the sink node there is a single path or a unique path. So, once we have these three assumptions, we have argued that this particular my sequence scheduling problem of such graph become polynomial time solvable. What does it mean? I can have an efficient algorithm which is polynomial time deterministic algorithm, which can give my optimum results in polynomial time. Okay. So, one of this algorithm is called Hughes algorithm. In today's class, I am going to discuss about this Hughes algorithm. Okay. So, so I have already discussed. So, this is the structure called tree, because from any node there is only one path, but these structures are graph because you can have many paths from one node to other node to the sink node, right. You can understand that. So, today I will assume that my sequence graph structure is this, and the delay of the node is basically all 1 and all are type 1. So, I do not have to bother whether it is a multiplier or a adder or a divider, right. So, I will assume that all are of same type of operations. So, the structure of my input sequence graph is basically is this, not this or this. So, once this is given, what I am going to show, that I am going to explain an algorithm called Hughes algorithm, which solve this problem in very fast in order of n time, and I am going to show that this always achieve the minimum latency for a given resource constant, and also for a given resource constant it always is the minimum latency. So, that I am going to show the intuitive proof for that. Okay. So, let us discuss the Hughes algorithm now. So, for Hughes algorithm I need to label the nodes. Okay. So, let us understand how we label the nodes. So, we are going to label the nodes using the distance of the node from the sink node. Okay. Let us try to do that. So, so this is my sink node. So, the distance from this node is 0 and this is given by alpha. So, alpha n equal to 0. So, this is my node 5 and the distance is 1. So, this alpha 5 is equal to 1. For this node distance is 2, 1 and 2. So, this is alpha 4 equal to 2. For this node the distance is 3, right, 1, 2 and 3. So, alpha 3 equal to 3, and for this node it is 4. So, alpha 1 equal to 4. Similarly, for this node alpha 2 equal to 4, for this node alpha 7 equal to 2, because the distance is 2. For this node is distance is 1. So, alpha 9 equal to 1. For this node alpha 11 equal to 1, and for this node alpha 10 equal to 2, and for this node alpha 8 equal to 2. So, this is how I am going to label each node, which is the nothing but the distance from the sink node. Okay. So, this is the labeling, and we identify. So, this is given by alpha I, right. So, alpha I is the distance of node V I from the sink node. Okay. And then I will just take this alpha, which is the max of all alpha I, right. So, where I equal to 1 to n. So, for this node what is the alpha, because see here the is 1, 2, 3 and all. So, the maximum value of this distance is 4. So, my alpha equal to 4, right. So, which is the maximum of all such levels. Okay. And then I am going to define another term P alpha I, which is basically, or say P j, right, or say P j, which is basically the nodes, the number of nodes have level j. Okay. So, have level j. So, that means I have to identify the nodes that has all the nodes of have level 4, similarly level 1 and level 2. So, for this graph, how many nodes of P4, how many nodes of having level 4? So, I have one node of level 4, another node of level 4. So, P4 equal to 2. So, the number of nodes that has level 4. Similarly, I can identify P3. P3 is basically one node, only one node, and for this node also 3, right. So, alpha 6 equal to 3. So, these are the two nodes having distance from the sink node is 3. So, there are two nodes which has level 3. Similarly, I can identify P2. P2, how many nodes are there? 1, 2, 3, 4, right. So, this P2 is 4 and P1 1, 2, 3 and P0 is the sink node. So, this is by the value. So, this is my initial processing. So, given this sequence graph which I know having satisfying these 3 assumptions that all node have unit delay, all have the same type and is it actually tree. I will identify first the alpha I for each node and then I will find out what is the maximum alpha I, which is alpha, and then I also have the P. P is the level, and you have to keep in mind that Pj is basically the number of nodes that has level j. Okay. So, this terminology is very important to understand the correctness of the algorithm. So, this I am going to do at the start, right. So, this is done. So, this for this information is available with me. Okay. So, now this algorithm is very simple. So, what it's basically does, you have given a resource A bar, say the because I have only one type of resource, I have said I have A bar number of resources, this can be 3, 4 or something. So, I say I have 3 multiprocessors or 2 multiprocessors. So, what I am going to do? As I mentioned in the previous class that for this kind of problem, because it is a tree, I can actually take a local decision, right. So, but when you basically if say for example, in this graph, so there are 5 nodes. So, I am going to try schedule the timestamp 1, there are 5 nodes which is schedulable, right, and say suppose my A bar equal to 3. So, among these 5 nodes I can take only 3 nodes, I can schedule only 3 nodes. So, there are many choices, right, 5 C3 possible choices are there. So, you can actually take any 3 from this 5, there are many choices which set to be taken, right. So, for generic graph this choice is not unique and it is not possible to take such decision at this at the timestamp 1. But for tree this particular choice is unique and this particular, I mean, we can actually take a local choice decision and I can actually show that if I choose that the choice that I have taken at the timestamp 2 will ensure the optimal schedule in terms of the latency or the number of timestamp. Okay. So, now the question is that I understand that say I mean for this node there are 5 nodes can be scheduled in timestamp 1 and say resource bound is 3. So, I can only select 3 of them, but how to select? To select this I am going to use this level. So, that is how I have calculated this, right. So, once I am going to say I have 5 nodes, I have to select 3, I am going to select all these 3 which has the maximum level, right. The sum of level of my selection will be maximum among all possible selection, right, and which is very simple that you basically select what is the highest value. And why this particular choice is give you the correct results if you try to understand that way, because say for example, here I have that selection is 4, 4, 3, 2, 2, right. So, I have to select say 3. So, I obviously going to select 4, 4 and 3 because that is summation will be 11. For any other choice the summation will be less, right. And why this is correct? Because this 4 is what? The distance of this node from the sink node. So, that means if I, because there are many nodes which is actually lying vacant or to be scheduled which is subsequent to this node 4, right, with the level 4. So, that means if I delay this operation further, So, then means this all the scheduling of the all the nodes which is following this node will be delayed, right. Here for this node there are 2 nodes to be scheduled after that, and for this node there are 4 nodes to be scheduled after that. So, obviously, I should select the node which has many nodes to be scheduled after that, right. So, that means my choice of selecting the maximum levels gives me the best solution, because I am making sure that the subsequent node will get earliest possible time to schedule, right. So, that is why this choice based on the level actually gives you the best solution when we can prove that. Okay. So, the algorithm is very simple, that I will start with my start stem 1, and I will identify the all the operations which is schedulable, right. So, in the sense schedulable means what, whose predecessors are already scheduled, right. So, that means they are already done. I am going to select such set. Okay. Let me just explain here. So, I will start. So, I have given this sequence graph and some resource bound. Initially, I will do all the labeling, right. So, this part is done, and this is my actual algorithm. Okay. So, now I have to identify all the nodes which is actually whose predecessors are already scheduled. That means, these operations are ready to be scheduled now. Okay. I will identify such nodes, and then as I mentioned that among these nodes which is actually schedulable, I have to select a subset of such nodes such that my resource bound satisfy, right. So, I am going to select a subset of this all schedulable nodes which is S, such that by the number of such needed node is less than of the resource bound, and I can actually show how I am going to select this subset and sorry. So, how I am going to select this this subset. The way I am going to select this subset is that this must satisfy the resource bound, and the level of the my selections is the maximal, right. So, that means, whatever the node I am going to select from this U, the summation of their level will be maximal among all possible selections, and since this nodes has some delay. So, I can actually always select the maximum values, right, which is very easy way to do that. Okay. So, whenever I just select this, I am going to schedule this S in this timestamp L, right, and then I will just increase the timestamp to L plus 1. I am going to do it for next timestamp, and I will keep doing this until my last node or the sync node is finished, right. So, you can understand the complexity of this algorithm is kind of order of n, because every time if you select a subset, they will be scheduled, and the next time I can actually just access there. So, I can easily, if there is a edge like this, and if it is scheduled here, I will just put this node as the in U for the next iteration. So, all node will kind of consider schedule. So, in every time, so the number of nodes is n. So, this kind of this algorithm will run in order of n. Okay. So, let me just give this example. Say for example, for this graph. So, the node, the number inside the node is the distance or the level, right. So, these are the levels. Okay. So, for U, so I am now in timestamp 1, right, timestamp 1. Okay. In timestamp 1, what is the U? Obviously, I understand the node 1, 2, 6, 8 and 10, right. So, these are the nodes which is schedulable, right. So, I will just mark them. So, these 5 nodes are schedulable, and say my resource bound is 3. So, which one I should select? I am going to select these 3 nodes among them whose levels are maximum, and I have already discussed that for this case I should select 4, 4, 3, right. So, then my S will be 1, 2 and 6, these 3 nodes, right. So, I am going to select these 3 nodes, because their summation of the delay is maximum. So, I am going to schedule them in 1, right. So, that means in timestamp 1 I just schedule these 3 nodes, right. So, understood. So, this is what I am going to do. So, this is my timestamp 1 is done. In timestamp 2, what is my U? What are the nodes? So, this 2 has not scheduled. So, they are still available. So, 8, 10, and now since these 3 nodes are scheduled, now 3 and 2 is also scheduled, I mean is available. So, these are the nodes is ready to be scheduled. So, these 4 nodes, right. So, these 4 nodes are ready to be scheduled. So, I can select 3. So, which 3 I should select? Obviously, I am going to select this node because this has delays 3. So, this node is basically operation is 6 I guess, this is node 3, and among this, these are all 2, right. I can select any 2. So, even it can be 7 8 or 7 10, that is you can just select arbitrarily, it does not matter. So, let me select say 7 and 8, right. So, that means in the next clock I just schedule these 3 operations. Okay. So, now this timestamp 2 is done. So, what is the timestamp 3? What is my u? So, now this node is yet to be scheduled, this is yet to be scheduled, and so this was still available from the timestamp 1. I am not scheduled, although it is available from timestamp 1, I did not schedule it timestamp 1 or 2 because it has low value, low level, right. And once you schedule this, these three nodes are not available. This node is not available because although this data is available, but the other data is not available. Until all its predecessors are done, I cannot schedule this node. So, these 3 are available. So, my u is basically 4, 9 and 10, and I can select 3. So, there are 3 nodes, I have to select 3, I am going to select all of them, right. So, because there are 3 resources are available. So, I am going to schedule this these 3 nodes in timestamp 3, right. So, once you do this in timestamp 4 now, TS4, my u is basically only these 2 nodes, these are the 2 nodes are now available. So, which is basically 5 and 11. Since I have 3 resources, I am going to schedule both of them, right, 5 and 11. This is going to happen in timestamp 4, and obviously in timestamp 5 the sync node will be scheduled, right. So, that is what is the execution of the Hughes algorithm in this particular example, and it is very simple algorithm, you understand, but this is very powerful example for this assumptions, right, because it always give you the minimum latency. Okay. So, as I mentioned that this is a very simple algorithm, but its very power lies the fact that it always give you the optimal solution. That means, once you assume that there are 3 resource available, so it give you 4. So, it gives the 4 timestamp, and this is the best solution for this, right. So, this is the 4 timestamp is given, and this is the lambda is equal to 4. You cannot schedule this less than 4 using 3 resources. Okay. So, that something can be proven that for this graph with 3 resources, lambda equal to 4 is the minimum possible value. Okay. In the other way, we can also show that when this lambda equal to 4, you need at least 3 resource to schedule in 4 timestamp. That is also the other way of thinking this, and Hughes algorithm is something is so powerful because it satisfy both, right. So, it is basically one hand it is a MRLC and other hand is also MLRC, because once you given a lower bound of the resource, you always optimal schedule or the optimum latency for a given resource, right. Similarly, if you just given this this is basically I have written here is that this is latency constant. So, if you are given a latency constant lambda, it always give you the minimum resource bound, and similarly here if you give a bound resource bound a, it always ensure that it actually schedule in minimum number of lambda. Okay. So, this is what the beauty of this Hughes algorithm. Okay. So, now what I am going to show is given such sequence graph which is has 3 assumptions is true, it is a tree, all operations are a unit delay and all of are same type. So, can I identify the lower bound for a given lambda? Okay. So, if I say I give you 4, can you identify that for lambda equal to 4 a bar is 3, right. So, can you identify this? So, we can actually for any, so now if you say if lambda equal to 5, what will be the a bar? So, can we have some proof or some equation which actually can give you the lower bound of the resource for a given latency. Okay. So, I am going to show this with this equation. So, this theorem 1 actually captures this, that if you have given a latency bound lambda which is this, I can actually identify the lower bound of the resource using this equation. I am going to explain it. So, this a bar is the lower bound of the resource needed to schedule with latency lambda. Okay. So, this is very important because I can actually given a lower lambda, I can always identify what is the minimum number of resource needed to execute this. Okay. So, let us try to understand this equation now. Okay. So, you can see here that there is a so what is given to me, I know this alpha value, right. So, because alpha was the level of the node, okay, so maximum level, right. So, in this particular equation let us try to understand what is known to me. So, this is known to me, right, because this is the latency bound is given to me. This alpha is the maximum level of the nodes, that is also known to me, and this p value is also known to me, because p of 4 is basically the number of nodes which has the level 4, p of 3 is the number of nodes which has the level 3, and so on. So, this all are known to me, only thing is not known to me is the gamma, right. So, this gamma is some constant, right. So, it is a integer constant. So, we need to find out some value of gamma, it can be any integer value. So, gamma is actually a positive integer greater than 0. We have to identify the value of gamma such that this expression gives you the maximum value. So, that identifying this gamma, right, is the things that you have to do, right. So, identify the value of gamma, right, sorry, this gamma which give you the max value, right. So, that is the things we have to do. So, now let us try to go into little bit more, right. So, since the value of this gamma can be 1, 2, 3, 4 and so on, let us try to put those values. Okay. So, let us say I put gamma equal to 1. So, how this equation looks like? So, if you put gamma equal to 1, this is the summation is basically become p alpha plus 1 minus 1, right. So, this become p alpha, and if you put gamma equal to 1 here, and this so for this example you remember, so I sell my lambda equal to 4 and I know alpha is also 4, right. So, this is 1 plus 4 minus 4, right. So, which basically this is alpha equal to 4. So, this become P 4 by 1, right. So, that means the number of nodes having level 4, and in my example such node is 2, right. So, this will give me the value 2, right. So, when this gamma equal to 1, I get a bar equal to 2, right. So, my a bar equal to 2 when gamma equal to 1. So, now let us take gamma equal to 2, right. So, a bar when gamma equal to 2. So, if you just put this value, so it is a summation, right. So, when you it is a summation, you have to consider both the thing, right. So, when gamma equal to 1, I know this is P 4, when gamma equal to 2, it is basically P 4 plus 1 minus 2, so it is P 3, right, and here this is 4 minus 4, it is 2, right, because this is also 4, this is also 4, it is whatever the gamma. So, what we understood, it is basically the average of the nodes, number of nodes which has level 2 and the number of nodes which has level 3. So, in my example it was 2 plus 2. So, this is 2 plus 2 by 2, which is 2, right. Now, let us try to put gamma equal to this say a bar when gamma equal to 3. Okay. So, let us try to understand. So, when gamma equal to 1, I know it is P 4, when I put gamma equal to 2 in this equation, j equal to 2, it is P 3, and if I put gamma equal to 3, it is alpha minus 2, which is 4 minus 2 is P 2, right, and here it is always this gamma is 3. So, it is basically the average of the number of nodes have level 4 plus number of nodes having level 3 plus number of nodes having level 2 by 3. Okay. So, this is basically identifying all such values, and then you try to find out the maximum value of gamma. I am going to consider that gamma for which this expression has the maximum value. So, if I take this graph, so as I already explained, for gamma equal to 1, this is my gamma equal to 1, this is already I have explained gamma equal to 2, this is my gamma equal to 3, and it is gamma equal to 4, right. So, this is, I mean, I have not shown, but you can understand this is how things will go. So, and I cannot go beyond and then gamma equal to 5 is this, right. I cannot go beyond gamma equal to 5 because then this there is no minus value, right. So, this will become minus and which is not defined, right. So, if you put gamma equal to 6, this will become p plus 4 plus 1 minus 6 become p minus 1. So, there is no p minus 1. So, I will my gamma also vary from 1 to 5. So, this is not true. So, I have to find out this the value of this, right. So, if I just put this value because I know the values of these nodes P4 and all. So, if I just put this value, it will come the max of 2, 8 by 3, 11 by 4 and 12 by 5, which is since it is a ceiling because you cannot have a resource which is point. So, it is basically 2 you can write this way, right. So, 2 max of 8 by 3 is also 3, 11 by 4 is 3 and 12 by 4 is also 3, right. So, or you can actually this is 2 it is fine. So, this is basically comes to 3. Okay. So, I need 3 resources for to schedule these things in 4 time step. So, that is what this expression gives you, and intuitively if you understand this is basically either you identify the nodes that having you need to identify the resource needed to schedule 4 the number of nodes which has the level 4, or you identify the nodes which has level 4 or level 3 and you take average, or you identify the nodes having the level 4, 3 or 2 and you take average. So, this will be 3 here, and or you take the nodes which has level 4, 3, 2, 1 and you divide it by 4, you take an average, or you identify the nodes that having level 4, 3, 2, 1 or 0 and you take an average, right. This is what this expression does in high level. Okay. So, this is very important in the context of this lower bound. So, here if I given a latency, I can actually identify the this lower bound of the resource. Okay. So, let us try to prove this why this is this holds. So, I will just give you a very quick proof of this. Let us say I got the max value of for this gamma star, okay, because for this example my gamma star is actually 3, right. Because it is there are many possibilities, I assume that this expression will be maximum when my value of the gamma is gamma star. Okay. And let us say for I want to prove it by contradiction, that I want to say that no, I mean I can actually schedule the things less than a bar, right. I can actually I need say need a which is less than a bar. Okay. I need a number of resource which is less than the a bar that is given by this equation to schedule this behavior within lambda, right. That I assume. So, as a proof of contradiction, I assume that this my resource requirement is A which is less than of this resource bound given by this equation to schedule this behavior within the latency lambda. Okay. Now, let us see. So, I have assumed this is my resource requirement which is less than of the maximum, this is A bar, right. Now, let us try to understand one thing. So, suppose, so since there are a number of resource, right. So, how many maximum number of operation can be scheduled in timestamp 1 is a number of say a equal to say 3. So, I can maximum schedule 3 operation because that is the maximum number of resource. In timestamp 2 also I can schedule up to 3, maximum 3. So, if I just go this way, if I mean L timestamp, maximum operation can be scheduled A into L, which is very obvious, right, because in every timestamp maximum a number of operation can be scheduled and there are L such timestamp. So, maximum possible operation that is scheduled so far will be A into L. Okay. Now, if we assume this L equal to this, which is this part. Okay. So, if I assume this, then the maximum number of operation will be scheduled till this timestamp will be this into this, right. So, this into this, which is nothing but I am just bringing these things here, right. I am just putting this gamma star plus alpha minus this, right, gamma lambda plus alpha, right. So, I am just saying this is the maximum number of operation which is scheduled still this timestamp, okay. And what is this? It is less than this, I just get it from this expression, right, because I just move this part here. So, this part will come this side, right. This is what I have written here. So, what is this? So, this is basically, if you just put you try to write the summation, it is P4, right. So, because my alpha so or instead of 4 I should write alpha, because this is a generic proof, and if I put gamma j equal to 2, it is basically P alpha minus 1. So, when alpha equal to 1, it is P alpha. So, when it is gamma, so it is basically P of alpha plus 1 minus gamma star, right. So, these are the levels that are already done. I mean, this number of operations that are scheduled is must be this level. So, among this level, the way I do the Hughes algorithm, if I try to do this, this must be done, because this will be considered first, then this will be considered, because their level is highest, right. If you remember, when I do this Hughes algorithm, what I am going to do? I am going to choose the nodes that has the highest level, right, that I am going to do. So, if we assume that this summations, the number of operations that is scheduled till this timestamp is less than this, and among these operations, which is the operation that likely to be unscheduled, this must be this, the nodes with this level, because these are the highest level, this has the higher level, this must be done, right. So, since this is less than this, that means at least some of the node which has level this has not scheduled yet. Understood? Is very important point here. I am saying that the number of operations that scheduled till this timestamp is this, which is less than of this, and this is nothing but this expression. So, among this expression, the so basically what this expression says, the number of node having the level alpha, or number of node having the level alpha minus 1, and so on. So, alpha is the maximum level. So, this is the nodes with maximum level, this is the node with the next set of levels, right, and so on. So, among these, since this nodes this delay has less than this, so that means among this node I can safely assume that at least one node with this level, the level with alpha plus 1 minus gamma star is still to be scheduled, because this is not scheduled. So, that means I have a node which level is alpha plus 1 minus gamma star is not scheduled yet. So, what this level means? That means the length of the path is this, right, this alpha plus 1 minus gamma star, and if since this is the length, that means at least to schedule the rest of the behavior I need at least this many timestamp, right, because in one timestamp I can only schedule one level, I cannot schedule multiple levels, right. So, what does it mean? To schedule the rest of the behavior I need at least this many timestamp, right, because this the length of these things, and so far I have taken my, I am actually L equal to this. So, total time will be this plus this, right. So, so as I mentioned that there are some node which has level this has not scheduled yet, and to schedule them I need this many timestamp, and I have already in L equal to this. So, I have total time will be this plus this, which I have written here. So, this is the my current timestamp, and this is the timestamp to be needed, and if I just do a summation, it is lambda plus 1. Okay. So, but then it actually contradicts our assumption, because I have said that I can schedule my behavior within lambda with A, right. I am assuming A which is less than A bar, but I have shown that if you take any resource which is less than A bar, your time will be taken is lambda plus 1, which is not lambda. So, that means my assumption is wrong, that whatever I have assumed that my A is less than A bar is a wrong assumption. So, A must be A bar, then only I can achieve lambda. Okay. So, this is how I prove it. I am not going to prove the other correctness, exactness of the Hughes algorithm, because lot of theory involves there. So, what this the exactness of the Hughes algorithm is important in the sense that if I give A bar number of resource and I can ensure that Hughes algorithm always give you lambda, and you can understand this A bar is depend on lambda, right. So, this is basically interdependent. For a given lambda, I can always identify the resource bound by this equation, and Hughes algorithm ensures that if I give this resource bound, so basically MLRC, it will always achieve the minimum latency possible which is lambda for this given resource. And similarly, if I given this lambda Hughes can schedule this behavior within lambda times time using a number of resources. So, which is basically nothing but M L R C. So, in general it is actually give a optimal solution for in both context, either it is MLRC or MRLC in both context. So, this is basically this is actually minimization of the latency under resource constraint, and this is this is actually MR, minimization of resource under latency constraint, because I am given this lambda or the resource latency constraint, and I am ensuring that I can schedule my behavior within lambda using a bar number of resources, and which is the lower bound. So, I can actually able to achieve the lower number of the lowest number of resource, hence is the optimal solution. And similarly, here for this MLRC, if I given a bar number of resources, I am ensuring that I am able to schedule this behavior within lambda, and lambda is something is the target is given, and for this lambda this is the minimum resource. So, that means this is actually able to achieve the minimum latency as well. Okay. So, this is why this algorithm is actually important, and one of the most another important aspect is that I mean obviously this my graph will not be tree for generic case. So, this may not be applicable for my practical purposes use algorithm, but as I mentioned in classes that for in practical perspective since this scheduling problem is NP complete, usually we go for heuristic algorithm, right. So, heuristic algorithm is something where we apply some heuristic, right, and those and one of the most popular algorithm is called list scheduling, right. So, this list scheduling actually inherited the idea of this labeling of the nodes from this Hughes algorithm. So, that is why I can actually make this Hughes algorithm generic for a generic graph using list scheduling, which is heuristic based solution, which may not give you the best solution always, but it actually is very useful, and in most of the practical purposes we usually apply list scheduling. So, that is why I covered this Hughes algorithm in detail, and which is the backbone of this heuristic based practical algorithm for generic scheduling problem. Okay. So, with this I conclude today's class. Thank you.